Thanks for the invitation. It's always good to be here. And thanks for coming despite of this cold weather. So today I'll talk about Ramsey numbers of cubes versus cliques. And this is based on a joint work with David Conlon, Jacob Fox, and Benny Sudakov. So Ramsey number, first introduced in 1930 by Ramsey, is defined as following. The Ramsey number of G and H is the minimum integer n such that every red-blue coloring of the complete graph on n vertices contains either a red copy of G or blue copy of H. So the most well-studied case is when G and H are both complete graphs. So if G and H are both a complete graph K sub K, then we define Rk as R of K against Kk. And it's known that this is between 2 to the 1 over 2, the K, and 2 to the 2. Okay. So this bound was known for about 65 years and essentially hasn't been improved. Only some smaller order term has been improved, but the main question here is to close the gap between the exponents. So here we have 1 over 2, here we have 2. It's a very big open question in combinatorics to try to understand what the correct behavior of this function is. At least we know that it's exponential. So that was one extreme when we had complete graphs. The graphs were really, really dense. But today I'll talk about the cases when graphs are sparse. So let's consider the following construction given by Fatal and Harari. Yes, Harari. So we put cliques, red cliques, these are red cliques, and they have size, number of vertices of G minus 1. And we put total chi h minus 1 of them, of these cliques. Chi h is a chromatic number. Then we put blue edges between all the cliques. So these are blue. So all the edges inside cliques are red, and between cliques are blue. And if you study this construction, first we see that no blue copy of H. Why is it? Because if you want to embed H, suppose we embedded H somehow. That will give us a chi h minus 1 coloring of our graph. So we can color the vertices of H by chi h minus 1 colors if we successfully embed H. But it's impossible because the chromatic number is chi h. That was one, so we forbidded a blue copy of H. And a red copy of H, as long as G is connected, if G is connected, no copy of G. Well, connectivity is a reasonable assumption, and if it's connected, then it has to belong to entirely inside one of the cliques, so we can't have a copy. This gives a bound, a very general bound. As long as G is a connected graph, we have the bound B of H is number of vertices of G minus 1 times the chromatic number of H minus 1, and then plus 1. Because we have a graph on this many vertices which does not have the Ramsey property. That means the Ramsey number has to be at least this plus 1. And so we can slightly improve it, rather meaningless, but a very slight improvement will be as follows. So this was noticed by...
That's for the connected graph.
Yes, connected graph G. For connected G. But all the graphs we consider today are connected, so this will be a general bound. And then Burr extended this bound as follows. So let sigma h be the minimum over all chi-h coloring of h, the size of the minimum color class, minimum size of color, minimum color class. So what does it mean? This number means that no matter how we color the vertices of h using chi-h colors, this is the graph h, and we color it using chi-h colors, no matter how we do it, every part has to have size at least sigma h. That's what sigma h means. If this is the case, then in this construction we can add a red clique of size sigma h minus 1. It's not a very spectacular observation, but still, so the general bound can be improved to RGH is at least number of vertices minus 1 times chromatic number of h minus 1 plus sigma of h. So this essentially followed from this by saying that sigma h is at least 1. Okay, so now let's look.
This bound looks incredibly weak. Is there any example where
that's exactly what I'm going to talk about today. So today we're going to talk about the cases when this is tight. Yeah.
So sigma is same as the minimum number of vertices which can be removed to reduce the chromatic number?
Yes. Yeah. So look at this. This gives exponential bound in terms of the number of vertices. Both of them have k vertices. But this is essentially polynomial. If you consider this to be the number of vertices, then it's just number of vertices of g times number of vertices of h, and it's polynomial. So there's a huge gap. But still, in some cases, this is tight. And so you can suspect that it should be the case that g and h are sparse, because the reason this became exponential is because these are dense graphs. And we will confirm this intuition. So Burr and Erdős noticed the same question is this bound tight in some cases? And we say that G is H good if the bound is tight. So in other words, if the Ramsey number of G against H is exactly that. And yeah. Then we also say that a family of graphs is H good if all sufficiently large graphs in G are H good. In other words, if we can remove a finite number of graphs from this family to make all the graphs H good, then we call this family H good. The reason we define it in this way is because we want to fix a family and look at for which graphs H this family is H good. So instead of imposing the condition that all graphs are H good, we just say that we just impose a condition that sufficiently large graphs are H good. And it will be clear why we make this twist, so add this a little bit freedom. Example. So stupid example. When h is equal to k1, all we can have is one vertex. So r of g of h is always 1. And this is always the case because chromatic number is 1 and sigma h is 1. But that is true because notice that chi h and sigma h are both 1. And also for h, k2, r of g of, k2 here, is number of vertices of g, because in this case we can never have a blue edge. Just having one blue edge gives a blue copy of k2, so we must have a red clique, and as long as we have number of vertices of g, many vertices, we will be forced to have a red copy of g. And this coincides with this bound because chi of h is 2. Because chi of h is equal to 2. And sigma h is equal to 1. And so the most interesting cases are when H are complete graphs. So for convenience, we say if it's KS good for some number S, then we just say S good. Because that is what we're going to study today. In which cases a seemingly weak bound is actually tight. Okay. So, Kvatal, I don't know how to pronounce this name that well, proves that all trees are S good for all S. This is slightly stronger than saying that the family of trees are S good. The family of trees is S good, because it says that every single tree is S good, instead of saying that it is asymptotically S good. On the other hand, if we change this complete graph into a different graph, it is no longer true that the family of trees is H good for all H. That means there exists some H for which the family of trees is not H good. So even though trees, what this essentially says that there is no universal graph which is good against every graph, except for these trivial things. The trees are simple. This says that trees are
for all H which are not complete graph?
So this is not a good statement. This no longer true that the family is H good for all H. That means there exists an H for which the family of trees is not H good.
Is this if and only if theorem, or is like family of graph is H good if and only if family of trees is H good if and only if H is
I don't know. I don't know. But I don't think so. Okay, so Burr and Erdős defined the concept of goodness. That was in 1983, I think. Yeah, 83, 81, and 83. And this theorem was actually proved before the definition of Ramsey goodness. So Kvatal already had the idea of that it will be interesting to study the graphs for which these bounds are tight, but didn't really systematically define the concept. And then Burr and Erdős posed a lot of conjectures and problems around Ramsey goodness to try to understand this concept. So one of the problems they posed, one of the most famous problems that they posed in this context is the following. For all delta and S, the family of graphs of max degree delta is S good. So if you look at bounded degree graphs, they should be simple enough so that this bound is tight. That was their conjecture. And they had one supporting theorem for this conjecture. And to see that, we have to define what a bandwidth is. The bandwidth of a graph G is the minimum L, such that there exists an ordering of vertices V1 up to Vn, such that I and J differ by at most L if Ij forms an edge, Vi, Vj form an edge. Forms an edge. That means we can linearly order the vertices so that all of the edges are really just close to each other. If we order the vertices, if you pick a vertex, it can only have edges within this L interval, L distance. And then what they proved was, instead of bounded max degree, if we have bounded, so for all L and S, the family of graphs, the family of bandwidth at most L graphs is S good. Note that if you have bandwidth at most L, you have max degree at most 2L. So this is kind of a partial case. A further restricted class in max degree is S good. Unfortunately, this conjecture is not true. Because it was posed in about 1980s, people didn't understand expander graphs so well. It wasn't that popular. And if graph shows expansion property, we can see that this conjecture is false. So Brandt proved that there exists graphs of degree 3 which are not 3 good. So it's not about the max degree. Instead, if you look at the proof, it actually proves that graphs with expansion property.
Three regular or
3 regular, yes. Expansion properties are not 3 good, or even S good. It's about the expansion property, so you can just take a 3 regular graph, generic 3 regular graph, random 3 regular graph, it will have the expansion property. So it's not good. But then, now this theorem looks a lot more interesting. Because bandwidth, having small bandwidth or sublinear bandwidth, is kind of the opposite of expanding. So this is equivalent to having no linear expanding subgraph. So I didn't quantitatively state this theorem, but people understand that if you have small bandwidth, then the graph is very far from being expander graphs. Itself is not an expander. Not only the graph itself is not an expander, also its subgraphs. We don't have subgraphs which are expanding subgraphs. And Brandt's observation, Brandt's construction, shows that graphs with expansion properties can never be as good. On the other hand, having bandwidth, if you have small bandwidth, constant bandwidth, then it is as good. So in some sense, this is very close from the truth. And these class of graphs are somewhere in the borderline. Recently, Allen, Brightwell, and Skokan improved that result by quite a lot. So they proved that for all delta and what was it? Yes. There exists a C such that all the family of graphs of max degree delta and bandwidth at most C times n is the number of vertices of the graph, is S good. So now this says a lot. It essentially says if you want to be S good, you need to be sparse and you have to not expand. This imposes the graph to be sparse and this imposes the graph to be non-expanding. Here, somehow, because we restrict the bandwidth too much, it automatically implied both conditions. But in fact, what happens is we don't have to impose such a strong condition. We can relax it like that.
What about planar graphs?
So later I'll explain it. But planar graphs don't really fall into this category. But there's another theorem.
Don't they have sublinear bandwidth? Planar
But they don't necessarily have max bandwidth. Yes. So there's a really similar theorem which kind of relaxes this condition but strengthens that condition, and that can be applied to prove planar graphs. Yeah, I will explain it soon. No, these are not infinite. We're talking about the family of graphs. So we look at all graphs which satisfy this condition, and there's only finite number of them which are not S good. So asymptotically, this family is S good. So it's not about individual graphs. Okay. So this theorem kind of really draws a finer borderline of being S good. And so one interesting graph that doesn't fall into this category is hypercubes. So if you consider hypercubes, planar graphs are an interesting family, but I'll later show it follows. It follows the corollary of some other theorem. So hypercube is a graph over the vertex set, over the vertex set 0, 1 to the d, where two vertices are adjacent if and only if they differ in exactly one coordinate. So for example, a hypercube of that's called a dimension 3 can be drawn like that, as the name suggests. So Burr and Erdős also asked, is hypercube, conjecture, this is by Burr and Erdős, is hypercube S good? So what I mean by this is a family of hypercubes S good for all S. Unfortunately, because the max degree grows, so the bandwidth of hypercubes, these have bandwidths at most, I think n over log n, but I'll just say little of n. But the max degree grows with the number of vertices. It's like log of n. So we cannot apply this theorem because the max degree just grows. So this is an attempt to go further in the borderline, trying to see what happens. And we studied this problem. We weren't able to quite establish the whole conjecture, but we're able to prove something similar in spirit. So that's Conlon, Fox, and Sudakov. What we showed was for all S, so there exists a constant depending on S, so C sub S, such that the Ramsey number of d-dimensional hypercube against the complete graph on S vertices is at most some constant times number 2 to the d. So if we want to prove the conjecture asserts that CS should be equal to 2. S minus 1. Essentially, up to some smaller terms. Because what we wanted was R of G of H is equal to the number of vertices minus 1, chromatic number minus 1, plus sigma H. But these are just all small things, so if you forget about it, it's just number of vertices of G times chromatic number of H. Chromatic number H minus 1. And this has chromatic number S, so it should be S minus 1 times 2 to the D, if we want to prove the conjecture. But this constant goes a lot faster than that. Still, the reason we think it's interesting is because it established the linear term, says that the Ramsey number grows linearly in terms of the number of vertices of the hypercube. And also, another reason this didn't follow from the previous approaches, previous tools we had was, here they use, regularity lemma and blow-up lemma. And so having max degree bounded is really essential. As long as it grows just a tiny bit, we cannot hope to apply the techniques. But what we did here was kind of brute force. It's really tailored to hypercubes, so we weren't able to extend it to some interesting family of graphs. But still, it says something about the borderline. Okay, so I will later show you some proof techniques of the S equals 3 case, so hypercubes against triangles. But before that, I want to discuss another theorem of this type. So now, what we're going to do is we're going to study so the degeneracy of a graph is defined as the maximum over all subgraphs of G, the minimum degree of G prime. That's the min degree. And then a graph is said to have a T eta separator if is T eta separator of a graph G is a set of vertices T of size at most T such that in the graph induced on V minus T, subgraph induced on V minus T have components, only have only components of size eta n, at most eta n.
Degeneracy, and what are you maximizing over?
Over all subgraphs of G. So an alternate definition is so if there exists an ordering of vertices, such that the number of edges going backwards is at most D, then we say that it has degeneracy at most D. So if you look at over all ordering the minimum number, that will be the degeneracy. So this, in an alternate way, we look at all subgraphs of G and wait a minute, that's not that should be equal to the minimum degree of the whole graph. Yeah. Right. So I think it brought.
This looks like unless it's a star, that number there is going to be the same as the minimum degree of the graph.
I think it's always is. So. Yeah. So I think I brought the wrong definition here. Sorry.
No, okay.
Minimum degree can't grow. No.
It can't grow.
It can't grow. So, yeah. So I brought the wrong definition. Sorry about that. So it's a minimum D such that there exists an ordering of the vertices V1 up to Vn such that Vi has at most D neighbors in the set V1 up to Vi minus 1. Maybe this is more transparent. So it relaxes the max degree condition. If we have max degree delta, then the degeneracy is at most delta. But if we have degeneracy delta, we can still have max degree huge. It can be like the whole. If you have a star, for example, then the degree is n, the max degree is n, but then the degeneracy is just 1. So now, as you can suspect, I'll erase it just to give you some comparison. Nikiforov and Rousseau prove the following. So for all S and D and gamma between 0 and 1, there exists an eta such that the family of graphs of degeneracy at most D and with a V sub G is 1 minus gamma eta separator is S good. Okay, so let's parse the meaning of this. First of all, it doesn't look that similar, but it's actually a very similar statement. Degeneracy is about the sparseness of a graph. We weaken the condition of fast degree. And separator is about non-expansion. So having a separator means that we can remove a small number of vertices to really tear apart the graph, make it into small connected components. And this says that we can remove really tiny amount of vertices because it's sublinear amount by a polynomial factor to really break down the graph into smaller connected components. And that is far from being expander. So this is a non-expansion part. But still, Lee's theorem doesn't imply each other. So there is no stronger or weaker. There are graphs which this cover where this cannot cover, and there's vice versa graphs. So as a corollary, what we obtained, we stated it as a theorem, but it really is just a corollary of this theorem is the following. So for all graph H, the family of graphs with no H minor is S good. And for all H and S. There's a theorem saying that if you don't have an H minor, then you must satisfy this condition. So, and this is slightly easier to apply. For example, planar graphs being S good just follows now, because Kuratowski's theorem really is about the minor. For example, we can apply this to say that planar graphs are S good, are in fact every non-trivial minor closed family is S good. Yeah. So, any questions? That was a history and state of art of S goodness. So essentially, and now if you go back to the first diagonal Ramsey number, it was exponential. In the number of vertices k, this was Ramsey number of k against kk. And now this really is really far from being sparse, R from being non-expander. Expands, like one vertex expands to the whole graph, and it's really, really dense. So that's why it's so far. Like the Ramsey number is so big. Kind of. I can't really make it mathematically logical, but it's kind of the intuition behind. On the other hand, when you get sparse, you can really get to this, where the trivial Ramsey construction is the right one. So now, yeah. Yeah, and what we studied was a hypercube. That's the main theorem in our paper. It's about trying to expand the boundary, trying to understand like what graphs are really S good, which graphs are not. So now I'll prove this theorem. I'll just erase this. That is the theorem we want to prove. The Ramsey number of hypercube against triangle is at most some constant times the number of vertices of the hypercube. So I don't think I can show the whole proof today, so I kind of simplified. What I'm going to show you is I can replace this C by a logarithmic factor, polylog. But then already this contains all the main ideas. So once you understand this, it won't be too hard to go back and read the paper to understand how the constant proof works. Okay. So now the proof. Not really the proof. Forget it, it's not proof. Suppose we're given a 2 coloring, red-blue coloring, of complete graph on n vertices. We don't know what n is yet. And we further suppose that there is no, without blue triangle. If there's a blue triangle, then it's already done. So we exclude blue triangles, and then we want to say that we always find a red copy of a hypercube. So case 1, just a simple case, simple case. If the number of vertices is already greater than d times 2 to the d, or d plus 1 times 2 to the d. So this is not a constant, even though this is c and this is d. D is not a constant. D is growing. C is a constant. So this is a weaker bound than that, but still this will be a very, very simple case. And what we can do is the following. Just arbitrarily order the vertices of the hypercube. And then greedily embed. Embed one at a time. Let's see what happens. When embedding the ith vertex, first, there exists at most I minus 1 vertices already occupied. Because we already finished embedding I minus 1 vertices. And then second, there exists at most d neighbors of, I'll call this vi, which are already embedded. For example, let's say we're trying to embed this hypercube of 3 dimension. And we finished embedding these 3 vertices, and we're trying to embed that. Now, we embedded this to some vertex, that to something, that to something. That means this is red, and that is red. If we want to embed this vertex somewhere, it has to be a red neighbor of that vertex and a red neighbor of that vertex. So, how many vertices can this forbid? And how many vertices can this forbid? It's at most a max degree. It's at most a blue degree of this vertex. Okay, so that observation is there. Then another observation is blue neighborhood of each vertex is a red clique. Because we don't have any blue triangles. If we have a blue neighbor, you have a vertex, and these are all blue edges, we cannot have any blue edges inside. That means it forms a clique. That means degree is at most, blue degree is at most 2 to the d, or less than 2 to the d. Because otherwise, we already have a clique of size 2 to the d, for which you can just automatically embed the cube. Now go back to this. I should have said that first. So there's I minus 1 vertex already occupied. And then there's at most d neighbors that we have to consider, but each neighbor can forbid at most 2 to the d images. So total I minus 1 plus d times 2 to the d minus 1 vertices forbidden as image of vi. In other words, all but these vertices are possible images of vi. Oh, we can see that I minus 1 plus d times 2 to the d minus 1 is at most 2 to the d plus d times 2 to the d, or less than, which is d plus 1 times 2 to the d. And that's the total number of vertices. So this is our basic strategy. We want to eventually go to the greedy process where we embed vertices one by one. But to remove this factor of d we have to be a little bit more clever than this. So now, I will assume that n is at least 32 times log d cubed times 2 to d. That's a strange number, but I picked it so that the computation gets most simple. Okay, there's 4 steps in the process. And I would like to reserve a board to write that down. So we want to prove that if n is greater than 32 times log d cubed times 2 to the d, then there's this red copy. Q, D. Step 1. Tile or partition QD. So what we're going to do for step 1 is I'm going to find a family of subcubes of QD as following. Log D. Oh, this is not as scary as it looks. So it's essentially a canonical decomposition. We fix the first log d coordinate and make the other coordinates free. So this is a collection of subcubes of the cube which have dimension d minus log d. So graphically, we're kind of breaking down our cube into this kind of shape. Because of the cube's recursive structure, for example, this will be 0, 0, 0, star, star. This will be 1, 0, 0, star, star. This will be 0, 1, 0, star, star. That will be 1, 1, 1, star, star, like that. So this is a breakdown of a 5-dimensional cube. I make it into a collection of a 3-dimension. I make it into a collection of 2-dimension cubes arranged in a 3-dimension cube. So we change the first coordinates, we fix it, and then make these coordinates free. And we choose log d of them. So we're exploiting the hypercube structure being recursive. And then what is the property? Is first, each cube in the family is adjacent to exactly the other cubes, or log the other cubes. In this case, I mean, it's not the right, there can be more stars behind, but each cube is adjacent to 3 other cubes because we're fixing the first 3 coordinates. We're arranging the cube in 3-dimension cube. Each cube is adjacent to 3 together.
What is this tiling? So you're just partitioning the vertex set in this?
Yes, partitioning the vertex set.
So you made a lower dimension hypercube.
Yes, so I break down into lower dimensional hypercubes, but it's also arranged in a hypercube shape. We have to exploit that fact too.
But I mean, where you pay attention to the edges that are going between.
Yes, we are only going to pay attention to the edges going between, essentially, later.
Okay.
Yeah. And so in this sense, what I mean is, if I take a hypercube in this arrangement, there is at most log d other hypercubes, which are even, which share any edge between them at all. Yeah. And another observation is for all vertex, so for all cube and all vertex in this cube, there exists exactly d neighbors of v, sorry, log d neighbors of v, not in C. So if you fix the vertex here, it has log d neighbors outside, each in the adjacent other cubes. If you want to look at it from this coordinates, what we get is, if we fix a cube, we obtain adjacent cubes by switching the coordinates. By switching one of the coordinates, we'll obtain an adjacent cube. So, kind of have that picture in mind. We broke down the cube in that way. And then we're going to use this observation. The neighborhood of each vertex is a red clique. So take collection of red cliques of size 2 to the d over d times 4. This number is chosen nicely. Don't pay too much attention to the numbers, it's the ideas. And take the maximal collection. And this side is exactly this. So we have a side red cliques. We call them S1, S2, S3, so on. We took a maximal collection. Last one is ST. And then there's some leftover vertices, n prime of them. Now here's a claim. First of all, in the remaining vertices, the maximum blue degree is less than 2 to the d plus d2 over d. Why is that? Because if you have a vertex whose blue degree is at least this number, then its neighborhood forms a red clique. That means we can take another red clique and add it to the family. So if we took a maximal family, this part has restricted maximum blue degree. And what it says, if we go back to the proof, if we plug it back, that argument to the proof, this implies that n prime is at most the max degree, blue max degree, times d plus 2 to the d. That's this formula, but revisited. That came from the max degree, max blue degree. So by using this exact same argument, we can obtain that the number of remaining vertices is only this much, which is 5 times 2 to the d. There's only a small number of vertices remaining. So now that means most of the vertices should have been covered. That means t times 2 to the d plus 2 over d. That's the number of vertices covered. Number of covered vertices. And this has to be at least n minus n prime. What was our n? Our n was 32, that strange number. I'll just half it. And we have 16d log d cubed to the d. Yeah. That means t is at least oh, sorry. There's no log d here. So t is at least 4 times d log d squared. We have quite a, that just means don't pay too much attention into what this numbers actually mean. It's more about how many vertices this red cliques cover. It covers most of the graph and only a small proportion is left out. So what our strategy will be is the following. We have these red cliques. We want to find arranged red cliques, nice. We want to find nice cliques, nice selection, and arrange it like following. So what this means is between these edges there is small blue density. What we hope to happen is we just put this small part in here. You can put it in an arbitrary way because these are each red cliques. No matter how we put it, this is just right. We put it here, we put this here, that here. And we hope that the edges going between them are also right. So that's our strategy. We have a collection. Now the next step is to choose a nice selection, which can be arranged in this way, so that between every two adjacent, not adjacent in this sense, red cliques have small blue density. And then we want to embed it like that. So that was our step one. Step two is find sets Si arranged in hypercube form so that adjacent sets have blue density at most 1 over 8 times log d square SISJ. Adjacent sets SISJ. So this is a quantitative amount we want. I want to arrange these sets like this so that the density is controlled. And how much we want to control it is this number. So I'll skip this step. And what we can next do is impose a max degree using this. Absolute degree. So from each set Si, remove vertices which have degree at least 1 over 4 log d times Sj in at least one adjacent Sj. So have the following. You have these sets S. Let's draw the front. S2, S3, S4, like that. So I will remove from S1 the vertices which have large blue into S1, and I will also remove the vertices which have large blue into S4, so that the resulting set has controlled the max degree. So call the remaining part T sub I. So what we obtained is a little bit more refined sets T1, T2, T3, and T4. And now the max degree, each vertex has blue degree. If you just compute everything, 1 over 2 times log d times the size of the set. So there is some computation to be done, which I will skip. But now I further trimmed this picture. I trimmed away some of the vertices. And not only we have small blue density, we have max degree control. Okay, why is this good? Now I'll finish it off. So remember the greedy embedding strategy. Just pick one vertex at a time and try to embed it into this picture. I'll just draw the front 4 parts here. Remember, this is a hypercube QD. This is a complete graph K and colored. We want to embed it. So pick one vertex at a time and try to embed it. So when we embed this to here, nothing will happen. This part is a red clique. No matter how I embed it, I'll just obtain this part. Now when I'm trying to embed this into here, I don't have to worry about the edges inside. I only have to worry about the edges across. But if you pick this vertex, that means when I'm going into here, I just have to worry about one of these vertices, this vertex, bothering that. So the idea is following. In a greedy embedding, at each step, the number of forbidden images is at most number of neighbors in other cubes times the maximum blue degree, 1 over 2 log d t of j. Plus the size of this cube, it's a d over d. But the number of neighbors of this vertex in outer cubes is at most log d. Because how we arranged it, each vertex only has log d neighbors outside. That means there's log d at most. So what we have is we occupy at most half of tj, and then 2 to the d over d. And I just made all work so that this is less than tj. So if we just greedily embed the vertices one by one, we will never run out of available vertices. We can always embed it one by one. So it was kind of technical, but just remember that the hypercube, what we exploited was the hypercube recursive structure of hypercubes. And because it's recursive, the number of neighbors we have to consider just reduces by a significant amount. We don't have to worry about all the d neighbors of the vertex. We only have to worry about the log d vertex neighbors outside. That was the key idea. Okay, so I'll just conclude with some open problems. First is conjecture of Burr and Erdős. So we weren't able to finish it. It says, is hypercube S good? It's a family of hypercubes that's good for all S. What we just proved was that the Ramsey number shows a linear bound. But we didn't finish off the conjecture. And we have our own conjecture. So this is false. So the conjecture says, prove that, well, yeah. Hypercubes are C2k plus 1 good for all. For k equal 1, equivalent to cube versus triangles. So now instead of looking at the complete graphs, we just want to look at odd cycles. And it might look a little bit just strange to look at odd cycles, but it's quite a reasonable thing because it is known that in Ramsey theory, odd cycles behave quite similar to triangles. So when we look at longer odd cycles, we think this conjecture might be easier than establishing this conjecture for triangles. Maybe for some long cycle it will be easier to prove this. And the last conjecture, this is again a conjecture of Burr and Erdős, says that proves that Ramsey number of cube against itself is linear in terms of number of vertices of hypercube. So 2 to the d. So they didn't conjecture that this is good, Ramsey good, QD is Ramsey good, QD is QD good. But they conjectured instead that because these graphs are so sparse, the Ramsey number shouldn't be too big. So that's it. Thanks for coming and thanks for listening.